So imagine you were sitting in the pilot seat. You were low Earth orbit, or maybe you are drifting through the Lagrange points on a long-haul mission. It is quiet. Everything is nominal. And then crack.
A micrometeoroid.
Exactly. A piece of space debris no bigger than a grain of sand. But it is moving at 700 meters per second. That is supersonic. And at that speed, I mean, kinetic energy is mass times velocity squared. So even a grain of sand hits your hull like a .45 caliber round.
It is the absolute nightmare scenario for spaceflight. And historically, the engineering answer to that problem has always been mass. You build a thick shield, you add heavy ceramic plating, or, you add layers of Kevlar.
Right.
But every single gram you launch into orbit costs a fortune in fuel.
You want a shield that weighs effectively nothing but still.
But stops absolutely everything. Exactly.
And that is the specific dream we are chasing today. Now, for everyone listening, you already know the drill. You are the experts. You know two-photon polymerization.
2P.
Right, 2pp. You have probably spent hundreds of hours staring at your nanoscribe interfaces, tweaking your slicing parameters, or worrying about your laser power. You know how to print the lattices. But today, on this deep dive, we aren't talking about the print itself. We are talking about the alchemy that happens after the print.
We are talking about taking those delicate microscopic polymer scaffolds, the stuff that you could honestly crush with a sneeze, and cooking them into something that frankly should not exist.
Pyrolytic carbon armor.
Yes, armor that is lighter than plastic, stronger than steel, and can stop a supersonic projectile in a space thinner than a human hair.
It sounds totally like science fiction, but it is right here in the data. The source material for today's deep dive is a paper titled Quasi-Static to Supersonic Energy Absorption of Nanoarchitected Tubulanes and Schwarzites. It's dropped just recently, February 2026, in Advanced Functional Materials.
It's a massive collaboration, too.
Yeah, University of Toronto, Rice University, MIT, led by Peter Searles, Kulikal Ajian, and Tobin Filleter.
These are heavy hitters in the materials science world. And the mission of this paper and what we are doing today is very specific. We are going to look at two competing geometries, Tubulanes versus Schwarzites. And we will see how they handle stress across 12 orders of magnitude.
12 orders of magnitude. That is just a wild range.
It really is. I mean, we are going from a slow quasi-static squeeze all the way to a Mach 3 supersonic impact. And usually, materials behave very differently at those two extremes.
I want to flag something right at the top here, because I know you guys love the theoretical side of things. This isn't just about making stronger materials. There is a specific theoretical ceiling in physics called the Suquet limit.
S-U-Q-U-E-T.
Right, the Suquet limit. It is basically the speed limit for how strong a porous material is allowed to be. And one of the geometries we are discussing today doesn't just perform well, it bumps right up against that theoretical limit.
Which is incredibly rare. Usually there's a massive gap between theory and reality. But here, reality is catching up.
So let us get into the setup. We start with the material itself. You are 2PP pros, so we can skip the how to print tutorial. You have your silicon wafer, you have your IP dip photoresist, you print your structure. But the magic here is the pyrolysis. This is where you turn plastic into carbon.
Right. This is the critical step. You take these printed polymer lattices and you put them in a furnace. In this study, they heated them to 900 degrees Celsius in a nitrogen atmosphere. Now, for the uninitiated, you might think, why 900? Why not 1,000? Why not 2,000?
It is the Goldilocks zone.
Precisely. If you go too low, you don't get enough carbonization. You still have way too much polymer character. But if you go too high, say 2,000 degrees, you start graphitizing the material. The carbon atoms start to order themselves into perfect sheets. And you might think perfect sheets are good, but for this application, we want disorder.
We want the mess.
We do. At 900 degrees, you strip away the hydrogen and oxygen, though they did find about 12% impurities left over. And you are left with what we call a turbostratic microstructure.
Turbostratic. I love that term. It sounds like a component from a warp drive.
It does sound sci-fi.
But it actually describes the messiness of the carbon layers.
Yeah.
Right?
Think of a ream of printer paper. In regular graphite, those papers are stacked perfectly. You can slide the top sheet off easily. That is why your pencil writes, you are shearing off layers of carbon. In turbostratic carbon, imagine taking that ream of paper, crumpling it slightly, and then jamming it back together. The sheets are there, but they are rotated, twisted, and interlocked.
So they cannot slide.
Exactly. The technical term is that the slip planes are frustrated because the layers are jumbled, and we are talking crystallites only about 1.6 nanometers wide. They cannot slide past each other. That frustration creates immense strength.
But here's the paradox.
Right.
And this is what I really struggled with when I first started reading about pyrolytic carbon. Usually, strong and disordered in ceramics means brittle. If I have a coffee mug made of glassy carbon and I drop it, it shatters. It doesn't bounce.
Correct. In bulk, this material is a ceramic. It has a failure strain of less than 5%, it snaps. But we aren't dealing with bulk, we're dealing with the nanoscale. The wall thickness of these structures after shrinkage is between 600 and 800 nanometers.
The size effect.
It is. When you get down to that scale, the probability of having a critical flaw, a crack large enough to propagate, drops significantly. The material stops behaving like a brittle ceramic and starts behaving surprisingly like rubber.
That is the key mental image for this deep dive. A material that is hard as diamond, but deformable like rubber. And now, you have to decide what shape to print it in to take advantage of that weird duality.
Enter the contenders. In the blue corner, we have the Tubulanes, and in the red corner, the Schwarzites.
Let's break these down. Schwarzites are usually the darlings of the 3D printing world. If you look at any promotional material for a 3D printer, they are always printing these beautiful, bubbly, continuous curves.
They are aesthetically very pleasing. These are triply periodic minimal surfaces, or TPMS. Specifically, the researchers used the P-type in this study. Think of it as an infinite, smooth, open, pore sponge. Structurally, they are isotropic, meaning they're the same in every direction. Engineers usually love them because there are no sharp corners to concentrate stress.
Or so we thought. And then we had the Tubulanes. These look, well, they look like logs.
They are much more utilitarian. Imagine a forest of wavy, interconnected vertical columns. They are analogs of carbon nanotube forests. They are anisotropic, meaning they have a grain. They were designed to take a load from one specific direction, top down.
So we have the bubbly sponge versus the vertical logs. Both printed from the same resin, both cooked at 900 degrees, both made of this rubbery turbostratic carbon. They put them in the crusher. First test, quasi-static compression. The slow squeeze.
This is a strain rate of 10 to the negative third per second, very controlled. And this is where the Schwarzites, those elegant bubbles, completely failed the audition.
They crumbled.
They failed at a strain of about 6 to 11%. That means you compress them just a little bit and snap. Catastrophic failure.
Why, though? I thought the whole point of that smooth, minimal surface was to distribute stress evenly.
Ideally, yes. But in reality, when you compress a sphere-like structure, you create tension rings. Even though the surface looks smooth, stress concentrates in specific bands. Think of the equator of the bubble. Once a crack starts in that glassy carbon, it has nowhere to stop. The structure fails before the material has a chance to really stretch its legs.
Okay, so the sponge breaks. But the Tubulanes.
Total domination. They didn't just survive, they thrived. They reached failure strains of over 26%. They were squeezing down a quarter of their height without shattering.
And this brings us back to that Suquet limit we teased earlier.
Right. The Suquet limit is a theoretical bound. It calculates the maximum possible strength a porous material can have based on how much stuff is in it relative to the air. The Tubulanes approached that limit. They achieved a specific strength of 2.44 megapascals cubic meter per kilogram.
For context, the Schwarzites were sitting down at 0.75. So the Tubulanes are nearly 3 times stronger just by changing the geometry.
But the metric that matters for armor isn't just strength. It is energy absorption. How much energy can you eat before you fail? The Tubulanes clocked in at 321 joules per gram in this slow test. That is the highest specific energy absorption of any architected material ever reported in this class.
Ever.
In the literature for carbon-based nanoarchitected materials, yes, it is a new benchmark.
Because the logs allow the stress to travel.
Exactly. It is the column effect. When you push down on a vertical column, the entire length of the column supports the load. Every atom is doing its share of the work. In the Schwarzite, only the craters of the bubbles are really holding the weight, while the poles just buckle.
Okay, so if you were building a bridge for ants, you use Tubulanes. But we promised space armor. We promised supersonic impacts. A slow squeeze in a lab is one thing. A micrometeoroid moving at Mach 3 is a different beast entirely.
Usually, yes. This is the phenomenon of strain rate dependence. Most materials panic when you hit them fast. Polymers turn into glass, metals lock up, they get stiffer and more brittle.
It is the classic non-Newtonian fluid experiment. If I slowly put my hand in cornstarch and water, it sinks. If I slap it, it feels like concrete.
Exactly, that is sheer thickening. But here is the data point that made the researchers do a double take. They tested these pyrolytic carbon structures using LIPE, laser-induced particle impact testing.
Which is just the coolest acronym.
It is. They are basically shooting 10 to 14 micron silica spheres at the lattice using a laser pulse, and they are clocking speeds up to 900 meters per second.
For context, a 9mm bullet travels at about 380 meters per second. So we're talking double, almost triple the speed of a handgun bullet.
And when the particle hit the tubulane lattice, the material just didn't care.
It didn't get brittle.
It was strain rate independent. From the slow squeeze all the way up to supersonic speeds, the Young's modulus and the yield strength stayed flat. The material behaved exactly the same way when shot as it did when squeezed.
That is incredibly counterintuitive for a ceramic-like material.
It is, and it is the killer app feature. Because if you are designing a shield, you need predictability. You cannot have your armor changing its physics just because the bullet is moving 10% faster.
So let us look at the action movie results.
Yeah.
They fire the particle, it hits the tubulane shield. What happens?
At 651 meters per second, the particle hits the 12-micron thick tubulane shield and bounces off.
A bounce. A total restitution.
99% of the energy was absorbed or dissipated, and the particle was rejected.
We need to pause on the scale here.
Mm.
The shield is 12 microns thick. That is 1/5 the width of a human hair. And it just bounced a rock, moving at supersonic speeds.
It is staggering. They found the transition velocity, the speed needed to finally punch a hole through it, was 687 meters per second for the tubulanes.
And the Schwarzites.
They failed earlier. Their transition velocity was 624 meters per second. It doesn't sound like a huge difference, but in ballistics, that margin is life or death. The Schwarzites just could not handle the localized stress.
But the tubulanes had one more trick. Scaling. This is the part about layering, right?
Huh.
Because a 12-micron shield is great for protecting a microchip, but it is not going to protect an astronaut.
Exactly. They doubled the thickness. They stacked about 8 unit cells. And when they did that, the stopping power didn't just double, it scaled up massively. They stopped particles moving at over 1,000 meters per second.
Over 1 kilometer per second. That is Mach 3.
And the specific inelastic energy absorption, the amount of energy the material ate up while destroying itself, was 865 joules per gram.
I want to contextualize that number. 865 joules per gram. How does that compare to, say, Kevlar or steel?
If you look at the Ashby charts, which are the league tables for materials where we plot strength versus density, 865 joules per gram puts this stuff above bulk Kevlar, above steel, above aluminum alloys. It is in the absolute upper echelon of energy absorbers. And remember, it is mostly air. It is a lattice.
So you have a shield that is 80% empty space, yet pound for pound stops more energy than steel.
That is the power of metamaterials. You are engineering the space as much as the matter.
But the paper goes deeper than just observing that it works. They wanted to know why. We talked about stress distribution, but that is a macro explanation. The researchers wanted to see what the atoms were doing.
This is where the simulation team really earned their paycheck. They ran a molecular dynamics simulation with 1 million atoms. They literally modeled the atomic behavior of the carbon during the crush.
And what do the atoms actually do?
This is the aha moment. In the tubulanes, because the structure holds together longer, the graphitic crystallites, those little frustrated chunks of carbon we talked about, they actually rotate.
They rotate.
They reorient. The simulation showed a change in crystallite orientation of about -1.5 degrees. The atoms are physically aligning themselves orthogonal to the loading direction. They are flattening out to catch the blow.
Like a judo master turning their body to absorb an impact.
It is a great analogy. The geometry of the tubulane holds together long enough to force the atoms to cooperate. It buys time for the microstructure to engage.
And the Schwarzites.
Negligible rotation. The structure buckles and snaps so fast that the atoms never get a chance to help. It is a wasted opportunity. The macrostructure fails the microstructure.
That is such a profound insight for anyone doing 2PP work. You can have the best material in the world, this amazing rubbery carbon, but if your geometry doesn't support it, you are leaving performance on the table.
It bridges the gap between continuum mechanics, how a bridge holds weight, and molecular dynamics, how atoms bond. The tubulanes prove that the shape you print at the micron scale dictates how atoms behave at the nanometer scale.
So what does this mean for the future? We have this incredible material. We know tubulanes are the winner. We know it stops supersonic rocks. Why aren't we coding satellites in this stuff tomorrow?
Well, there is a catch. There is always a catch. It is the size effect we mentioned at the start.
Let us unpack that. Why cannot we just scale it up?
All of this magic, the rubber-like behavior, the strain rate independence, it relies on the struts being submicron. If you scale this up and try to print a tubulane where the logs are, say, a centimeter thick, you lose the magic. The carbon becomes a brittle bulk ceramic again.
So I cannot just take the STL file, hate scale 1000x in my slicer software, and print a helmet.
Absolutely not. If you want a big shield, you have to tile it. You have to print billions of these tiny unit cells side by side.
That is a manufacturing nightmare. 2PP is precise, but it is slow.
It is, but that is changing. With holographic printing, multi-beam systems, faster galvanometers, the throughput is increasing logarithmically. But right now, yes, making a square meter of this armor would take a very, very long time.
But for small things.
For microsatellites, for protecting sensitive sensors, for coding the optics on a space telescope, this is ready to go. It validates that the 900-degree pyrolysis route creates a stable, predictable, high-performance shield.
It really changes the way you look at a nanoscribe machine. It's not just for making tiny towers or microfluidic channels. It is potentially a forge for the next generation of armor.
It is. And it challenges the aesthetic bias we have. We love the Schwarzschites because they look organic and smooth.
Yeah.
But the tubulanes, the rigid, boring logs, are the ones that save the day.
Function over form.
Always.
Before we wrap up, I want to leave you, the listener, with a final thought. We have spent this whole time comparing tubulanes versus Schwarzschites. A binary choice. One wins, one loses. But engineering rarely works like that.
What are you getting at?
Well, we established that tubulanes are anisotropic. They are great when hit from the top. But what if the asteroid comes from the side?
That is a fair point. They would likely be much weaker laterally. The logs would just bend over or shear.
And the Schwarzschites, while weaker overall, are isotropic. They are the same from every single angle.
True. They offer consistent, if lower, protection.
So here is the challenge for you 2PP experts listening. What is the hybrid? Can you design a superlattice? Maybe a gradient structure?
Oh, I see where you're going. Maybe a Schwarzschild outer layer to catch off angle impacts and orient them, transitioning into a tubulane inner core for the heavy stopping power.
Exactly. Or a lattice that mechanically shifts its geometry upon impact. The paper hints that periodicity allows for scaling, but the transition from a homogeneous sample to a complex functional armor system is the next frontier.
And with the ability to print virtually any geometry, the only limit is the imagination of the designer.
The material science is done. The atoms are ready to rotate. Now they just need the right architecture.
The challenge has definitely been set.
Thanks for diving deep with us today. Check the show notes for the full paper from Searles and the team. It is worth a read for the SEM images alone. We will catch you on the next one.
Stay curious.